Alright, let's do more problems based on derivatives using first principle. And if you have watched my previous videos, you might have noticed one little difference in the way I have written the first principle. Usually in my previous videos I've written it as f dash of x. F dash, I said, was the little notation we use for derivative of the function, and then f dash of x is equal to whatever you see on RHS of this equation right here, right? But now you see I've written it as d by dx of f of x. F of x is still there, but I'm using a different symbol, d by dx. Meaning of this is that I'm trying to find the derivative of this function f of x. I'm trying to find the derivative of the function f of x with respect to x, meaning that I'm trying to find out whether this given function, which obviously is, look at the little f of x, suggests that it definitely depends on x, right? So at what rate with respect to x does the function change? For example, I'll just change the topic a little bit and please listen to this. Say for example, a function f depends not only on position but also depends on time, right? It depends both on position and time. Such a function, if you have, or let's say there is a function, forget position and time both, let's say there is a function which depends only on time, function depends on time and not on position, then if you were to find the derivative of this function with respect to position, meaning if I'm trying to find out whether this function changes with respect to position. Does it change with respect to position? And the answer to that is no, it does not change with respect to position. It does not change with respect to position. Then what does this function actually depend on? This function depends actually on just the time, right? And such a function, if you try to find the derivative of this function with respect to x now, if you try to find the derivation of such a function with respect to x, then what will happen is that it will not be depending on x. Then what will happen, that and all we'll see later. But yeah, the point I'm trying to make here is, it's not just knowing the first principle which is enough for you. It's not like it's always going to be just f of x, f dash of x. The actual question you should be asking is, f dash of x, fine, with respect to what, right? And I did not want to mention those in previous videos because we're not ready yet, right? But now we are ready, right? So the point I'm trying to make here is that say you want to find f dash of t with respect to position, or that's why it's better written like this, d by dx of, d by dx means you are trying to find the derivation of the function with respect to x, right? D by dx of f of t. If you are trying to find that, right, the answer to this actually would be 0. And why it will be 0, I'll take a little example and show you for why it will be 0. But in a nutshell, what I can say at this stage is that since this function since the function f of t does not depend on position, right, so the function will not vary as the position varies. So position can go on changing from 0 to whatever, to infinity or to minus infinity. Since this function depends on time, unless time is going to change, this function will not change, right? A time will definitely be changing, but at least with respect to x it will be constant, right? So let's try to find that with an example. For example, let's say I have a function which looks like this. Let's say f of x is 2. Now is that really a function? If you look at it, it actually is. F of x equal to 2 is basically this line right here. F of x equal to 2 is actually just this 1 2 3 4. F of x equal to 2 is this line parallel to x axis right there, this being my x axis, this is my y axis, or you can be like f of x axis, right? So f of x equal to 2 is just this line, right? Let me try to find the derivative of it. If I try using the basic principle, first principle, right? So f of x d by dx of that, d by dx of f of x, if I try to find that, d by dx is like a notation to write f dash of x. If I use a first principle, I'll just write f of x plus dx. So f of x plus dx would be, I'll have to substitute for the values, but the thing is look at the RHS, it does not really have, this function really does not have the variable x in it, right? So f of x plus dx, like for example, let's say x is 8, right? So f of x plus dx would be the function of 8 plus a small value after 8. What's the value of x? What's the value of f of x at x equal to 8? It is 2. So you can just write it as 2, right? So f of x plus dx is simply 2 minus f of x. What's the value of the function right at 8? This is a slightly 8 plus something, it was 2, and right at 8 what was the value? Still 2. Alright, so 2 divided by dx or whatever, but you will still get 0, right? So this tells me that if a given function does not change with respect to that quantity with respect to which you are trying to differentiate the function, then the answer will be 0. Or in a simplest way I can say this, that the derivative of a constant is 0. Derivative of a constant is 0, right? But wait, you must be thinking, so are you trying to tell that f of t, the function, is it a constant? No, that's not a constant function. But with respect to x, yes, it is constant, and that's why it is 0. I hope you understand, right? Fine. And I just wanted to emphasize on this point to just to show this, that derivative with respect to what is really going to matter for us. Not really at this stage, but at a later stage it will definitely matter to you in mathematics especially, and even in some physics problems. Fine. Now with this, actually I got carried away from the actual definition of the actual title of the topic, that is derivative using first principle. So I've already done one derivative with respect using first principle. Let's try one more, maybe sin x. Yeah, let's try this question. Find the derivative of a function f of x which is equal to sin x with respect to x using first principle of derivative. Alright, let's try that. So you all already know that first principle says this, that derivative with respect to x of a function f of x is basically f of x plus dx minus f of x whole divided by dx. That right there is your first principle, right? Yeah, let's try that. So your function itself is sin x, right? So let me d by dx of sin x is equal to, now I'll straight away substitute the values, right? So it's going to be, instead of, now you don't really have to write f of sin x or anything, whatever the function is, just substitute for that value. For example, f of x plus dx would be sin of, just replace x with whatever you see in the little bracket here. So sin of x plus dx, that's what the function is, right? Sin is the function. So yeah, minus, what is f of x? F of x is actually given in the question, which is sin of x whole divided by dx. So you only have to evaluate this and see if you get something with that. Fine, so I will not write the LHS a lot, I'll just focus on this. Let's evaluate this. This little sin x plus dx looks like, reminds me of sin a plus b. And what's the expansion of sin a plus b? It's sin a cos b plus cos a sin b, right? So if I do that, it will be sin x cos dx plus sin dx into cos x, sin a cos b plus cos a sin b, minus sin x, of course, minus sin x, this sin x right here, minus sin x whole divided by, just a second, whole divided by dx. All right, so that's what I'll call it f dash of x now. So it's understood that it is with respect to x as clearly mentioned in the question. All right, so f dash of x now is equal to, but before I can proceed any further, looks like this has a lot of dx's in it. Now I would like to mention, I have to mention, right, there is in this chapter of maths, later you will learn this in the chapter called limits and derivatives, that, and just agree with me when I say this, that if dx, or I'll just, if x is very small, if x is very small, then two things happen. Sin x can almost be written as x itself, and actually there is this little thing, there is this thing called Taylor series expansion, which you don't really have to know at this stage, but you can either use the limits for this, limits, you can either use limits to get at this value or Taylor series, but trust me when I say this, that you can write sin x as x, or you can also write cos x as 1, and this is true only for if x is very small, and we actually have something that is very small, except in this case I don't have x, I have dx instead, and we already know that dx is very small, right? So I'm going to use that. So f dash of x is equal to, sin x remains sin x only, sin x, I'm just evaluating this now, so you have sin x, which I have kept as such, cos dx, is dx small? Yes. And for what happens if cos of very small value is equal to 1, so sin x into 1, which is just sin x, plus sin dx, I came across sin dx now, is dx once again small? Yes. And what happens if sine of something very small is almost that very small value itself? So sin dx in fact can just be written as dx into the cos x will still be cos x minus sin x whole divided by dx. I think you can already see the picture. So f dash of x, the derivative of sin of x with respect to x, is sin x gets cancelled, you are left with cos x dx divided by dx. So dx by dx is just 1, and you are left with therefore cos x, and that right there is the derivative of sin x with respect to x. And in that little table of derivatives you clearly have this, that derivative of sin x is cos x. In fact, I encourage you to go ahead and try all the derivatives of all the values using first principle that you have there in the table. For example, I'd really encourage you to try these derivatives. Find the derivatives of following functions. Try this. Try to begin with, try to find the derivative of cos x, try to find derivative of log x, try to find the derivative of tan x, would be a little lengthy, but you can, if you have time, you can go ahead with that. Try to find the derivative of e to the x and so on. These three should be fine for now. Okay, yeah, that will be really great if you can try that. Fine. So yeah, there goes. So the point I'm trying to make here is that, you know, using first principles, you can arrive at the derivative of anything you like, right? But then you'll not always rely on, you'll never in fact rely on that for simple functions like sin x, cos x, log x, e power x, tan x, I mean a to the power x. In fact, there is this derivative also. This is going to be a little lengthy again if you try that, but yeah, you can just try this using the first principle. And there goes the first principle. In none of my videos will I give you that table. That those are all, you'll already be familiar with those things. Fine. So that there, right there, is the derivative of a function using first principle. And more importantly, I needed to discuss that how a given function's derivative depends on with respect to what you are finding the derivative. And one more small thing we learnt in this is that derivative of a constant is always 0. So you can in fact make your own table, you know, of all the derivatives that you have been finding. You know, here you can write the function, and here you can write the derivative of the function. And so far we ourselves have done two derivatives, right? One is derivative of a constant was 0. Derivative of x to the power n, in the video, 1 or 2 videos before, x to the power n is n into x to the n minus 1. Derivative of sin x happens to be cos x in this video. You can in fact go ahead and find the derivative of cos x. You can find log x, and so you can make your own table basically. In your free time, it's definitely a good idea to try that. It will give you a good grip on the first principle. Alright, thank you.